All right, so I had to cut that last video short. My 3-year-old needed something suddenly. Sorry about that. I'm actually going to start this example over again. We were working through our first example in this section, so I'm just going to read through it one more time. A mass weighing 24 pounds attached to the end of a spring stretches it by 4 inches. Initially, the mass is released from rest at a point from a point 3 inches above the equilibrium position, and we want to find the equation of motion. So this is where, if you have some background in, physics, even like an intro to physics class, you need to be careful with your units of measure, and they need to be consistent. So, first of all, the object that we're told about here is given a weight, 24 pounds. Weight is not the same thing as mass. Weight is a force, but it's directly related to mass. So we'll deal with that in a second. And then the units of length here are showing inches, but we're actually going to convert that to feet, and we'll talk about why in just a second. So first of all, the weight of an object is equal to the mass of that object times acceleration due to gravity. And that's actually just a consequence of Newton's second law. There's your acceleration, there's your force. So this implies that the mass of an object is equal to its weight over the acceleration due to gravity. In this case, the weight is 24 pounds, and in imperial units, the acceleration due to gravity is 32 feet per second squared, approximately anyways. So we go with 32 here. Okay, this will simplify to 3/4, and the units of mass in imperial units is the slug, so 3/4 of a slug. All right. Now, S, the quantity that we've been calling S in our derivation in the previous video, is the amount by which our spring is being elongated by the object that's hanging from it. So in this case, the string is stretched by 4 inches. S then is 4 inches. However, even though I didn't write it here, remember that 32 is measured in feet per second squared. So we're already using a quantity in which the unit of distance that's being used is feet. I can't mix inches with that. I need everything to be in terms of feet now. So this is the same thing as 1/3 of a foot. We have to make that conversion for things to actually work. Okay. Now, remember, right now, when we say that we've attached this weight and it's stretched the spring by 4 inches, that's what it takes for the object to be in the equilibrium position. It then talks about it being released from rest at a different position, but when it's first hung on this spring and is in the equilibrium position, it's giving us S equals 4. Now, when it's in the equilibrium position, our forces are balanced. So that means that the restoring force of our spring is equal to our weight. So we have this relationship. So remember, the restoring force of our spring by Hooke's law is negative kx, or sorry, negative ks. But because these forces are balanced, it's the negative of that negative. So it's positive ks now. And this gives me this relationship. K is equal to W over S. I'm doing this because I need to use K in the steps that follow. W, we know, is 24, and S, we also know, is 1/3 of a foot. This is equal to 72. The units here are pounds per feet, not pound feet. Okay? I don't really need those units anywhere else, but I'm going to write it down just so it's there. Okay? So that follows from Hooke's law. Now we have enough information to put together our equation of motion. So if you'll recall what we derived before, our equation of motion is this. The second derivative of x with respect to t plus omega squared x equals 0, and omega squared is equal to k over m. That's why we found m and k here. We need to use those. So our equation of motion is going to look like this. X of t equals That's the differential equation, but our solution will look like this. So x of t is going to equal c1 cosine of omega t plus c2 sine of omega t, where omega is k over m, or, in fact, let me do this. K over m is equal to, where did I find k? Right here, 72 over m, which is 3/4, which equals, that's equal to 96. And that's omega squared right there. So that means my solution will look like c1 cosine of just omega. If that's omega squared, then omega would be root 96t plus c2 sine of root 96t. Now, we're not done because that's a general solution, but we're given initial conditions here. So we need to actually go the extra couple of steps to figure out what C1 and C2 are equal to. So what can I discern from my initial conditions, or what are my initial conditions? It says initially the mass is released from rest from a point 3 inches above the equilibrium position. Above the equilibrium position, remember we think of that as the negative x-axis. So it's already given in, or it's given in inches, we need to convert that to feet. 3 inches is the same thing as 1/4 of a foot, but we're on the negative part of the axis, so we're going to call that negative 1/4, okay? X prime of 0, our initial velocity is 0, and that's because it says that we're releasing this from rest, okay? Now, we need to use these initial conditions. In order to do that, I need to know what x prime looks like, so I'm going to find that here. X prime is equal to negative root 96 c1 sine of root 96t plus root 96 c2 cosine of root 96t. Okay, now my first initial condition, x of 0 equals negative 1/4, implies that we have this. Negative 1/4 equals, plugging a 0 into x of t up here is going to give me sine of 0 here, which makes that go away. Cosine of 0 is equal to 1, so this whole thing reduces to just c1. Right away I have c1. X prime of 0 equals 0 implies that when substituting a 0 in here, I should have 0 equals, sine of 0 is equal to 0, cosine of 0 is equal to 1 times root 96 c2. That gives me this, 0 equals root 96 c2. Of course, if that's the case, then c2 would have to equal 0. c2 equals 0, okay? Finally, I can put my parameters in. X of t is equal to what? Negative 1/4 goes into c1, so I have negative 1/4 cosine of root 96t, and then c2 equals 0, which eliminates that entire term right there. So this is my final answer. That's my equation of motion. Okay? So, moving on. As we had said previously in the last video, the equation that we got for our solution, the function that we're getting as our solution to these undamped motion problems, look like a linear combination of a cosine and a sine with the same argument, omega t and omega t. And I had said in the last video that this is actually a sinusoidal function. What that means is that this, when graphed, is a sine wave. That may have had some compressions and shifts happening to it, but it's still just a sine wave. Which means in this case, we can actually put this in the form x of t equals a times sine of omega t plus phi, where the phi here will affect the phase shift of this trig function, this sine wave. If you remember from trigonometry, talking about phase shift. So we call that phi the phase angle, and then this a here impacts the amplitude of our sine wave. And again, amplitude is something you would have talked about back in trigonometry when you're talking about graphing trigonometric functions. You might need to do a little review of that because that's heavily involved in this section. Okay, what's the purpose of wanting to do this? Well, the amplitude of a sinusoidal function can be useful information. We can use it to directly find the extreme displacement, the extreme values of this function. but it's not immediately apparent from this form of our solution what the amplitude of the resulting sine wave would be. In this form, A gives it to us directly. So that's kind of the primary reason we might want to convert from this form to this form, because it reveals the amplitude to us. So how do we convert this to this? Well, let's start with the end goal. I would like to suppose that we have a representation for our solution that's in this form, and I want to see how this relates back to this. Okay, so what I'm going to do is use the sum identity for the sine function on this right here, because I have a sum of two things in my argument for my sine. From our sum identity for the sine function, this expression can be expanded like this: a sine of phi cosine of omega t plus a cosine of phi sine of omega t. All right. Now compare that to our original solution. Look at my first term here. I have c1 times cosine of omega t. Notice I also have a cosine of omega t in this term right here. So what that would mean, if these two things are to be equal to each other, that would mean that this a sine of phi right here has to be equal to that c1 right there. Similarly, this a cosine of phi right here needs to be equal to that c2 right there. So I set those two things equal to each other. And then if I divide both equations through by a, equivalently I could write this: sine of phi equals c1 over a, cosine of phi equals c2 over a. All right. Now, C1 and C2 do not have to be positive numbers, but if we just kind of think of them as positive numbers to put a visual to this, then I can associate these two relationships to a right triangle. Think of right triangle trigonometry. How do we define the sine of an angle? It's opposite over hypotenuse. How do we define the cosine of an angle? Adjacent over hypotenuse. And notice we have the same hypotenuse occurring in both of these. So these all kind of belong to the same right triangle, which I've represented here. This is from your book. Okay, here's your angle, and based on what we saw on the previous page, the side opposite that angle phi would be C1, the side adjacent to it would be C2, and then this hypotenuse, we were calling that A on the previous page, but knowing the two legs of this right triangle allows us to find that explicitly in terms of C1 and C2. So that would be equal to the square root of C1 squared plus C2 squared, just by the Pythagorean theorem. Therefore, that A that we were looking for, that would give us our amplitude, is just equal to the square root of the sum of the squares of your parameters, C1 and C2. Not only that, the angle phi, your phase angle, has this relationship. Tangent of phi is equal to C1 over C2. Okay, which we see again from the relationships in this right triangle. So let's see if we can apply this. We have another spring mass system. This is our next example. And this time we're lucky. We're given the equation of motion right away. Usually, most, if not all problems you do in this section, you have to come up with this first. But we're given this right away. And we want to determine the alternative form of this equation that we just showed, the sinusoidal version, and identify the amplitude of that function. So again, the sinusoidal function looks like this. This is the form we're trying to put our equation into. And in order to do that, we already know omega. Omega is 3, because that already appears in this form of the equation. But we need A, our amplitude, and phi, our phase angle. And these two relationships tell us how to find that. So looking at this form of the equation here, of our solution, C1 is equal to 4, and C2 is equal to negative 6. Okay? Now, where was I? Oh, yeah, so we want to use these two values to determine A and phi here. So let's start with A. A then is going to equal 4 squared plus negative 6 squared, all under a square root. This would be equal to, after working that out, I lost my place in my notes here. That's all right. That's 16 plus 36, which is 52. That's square root of 52. Okay, I'm not going to worry about simplifying radicals. I'm just going to leave it in this form right now. And then tangent of phi is equal to C1 over C2. So that's 4 over negative 6. Now, I want phi explicitly. And your first instinct is probably going to be to take an inverse tangent of both sides of this to solve for phi. You do have to be careful with that, though. And the reason why is because the inverse tangent function, remember, has a restriction on its range. It can only give you angles in the first or fourth quadrant of the unit circle. But there's no reason phi needs to belong to one of those two. So for example, if I took the inverse tangent of this, if I took the inverse tangent of, this is the same thing as negative 2/3 here, I get a number that's approximately negative 0.59, okay? Now, if I think about where that is based on the restriction, this is in radians, first of all, that would put my angle in the fourth quadrant. But does phi actually belong in the fourth quadrant? Well, remember, we have these other two relationships over here that we're using. And C1 in our problem is a positive number, and C2 in our problem is a negative number. That means sine of our angle is positive, cosine of our angle is negative. That only happens in the second quadrant of your unit circle. It doesn't happen in your fourth quadrant. You would have the reverse of that. Tangent is also negative in the second quadrant, so we actually need this to be an angle in the second quadrant, not the fourth quadrant. And because tangent has a period of pi, we can simply add pi to this. So phi is equal to negative 0.59 plus pi. I think I didn't write my answer down, unfortunately. I think that comes out to something that's like approximately 2.55. So what that means is that we have our amplitude now, which is here. Notice that was one of the things that we were asked for in this problem, but we can also put the information here together to find our sinusoidal version of this function. So our function now, x of t is equal to our amplitude, which is root 52, times the sine of omega t. Remember, omega is just 3, it's already there, plus 2.55. Again, that 2.55 is an approximation, but that's good enough. So now if you were to want to check your answer here, obviously you can go into a graphing calculator, graph both of these functions separately. You should be seeing the same graph, or at least something so close because of that approximation right there. It's not exact. So close that it's enough to see that they're the same thing. Okay? All right. We're going to move on to another version of what we have been talking about up until this point, still spring mass systems, but what we're going to do is increase the resolution of our model. If you remember back when we were in chapter 1, we talked about what that means when you find a mathematical model for a physical phenomenon, and you start with kind of ideal conditions, ideal circumstances, come up with a mathematical model, and then test that against an experiment or data and see how good your mathematical model is. And if there seems to be too much error involved, you increase the resolution by adding additional assumptions to account for the variables that are occurring there. So that's what we're doing here. The motivation behind this, we're going to be calling this free damped motion compared to free undamped motion. The motivation behind this is the fact that in a system like what we're talking about, hanging a mass from a spring and releasing it and letting it oscillate up and down, so far we've only considered two forces on that object. There's the force due to gravity, and then there's the restoring force of the spring. But in reality, there would be an additional force that we'd have to take into consideration, and that's the force induced by the surrounding medium. So what we mean by surrounding medium is if this is a spring that's hung from a ceiling in a room, for example, the surrounding medium is the air in that room. There's no reason why we couldn't consider a spring mass system that's submerged under water or some other fluid, and in that case, the water or the fluid, that's going to be the surrounding medium. That surrounding medium creates a resistance to that force. With air, we commonly just call that air resistance. But the same thing occurs in other fluids. So the key thing about that resistance is it is a force. That's what a resistance would be, is a force. And it's always going to act opposite. It's always going to impede the motion of that object. So it's not always acting downward or upward. It's going to be acting opposite the direction of motion at any given instant. Okay. Not only that, we know from experimental data, and I'm going to kind of explain why this is a reasonable assumption to make. We know that the force, that resisting force from your surrounding medium, it's directly proportional to the velocity of your object at any given time. So the faster your object is moving, the greater that resistance is going to be, and vice versa. And this is something that you should expect just from your experience in real life. If you can imagine sticking your hand out a window, which I think everybody's done, sticking your hand out of a car window while you're driving. When the car's moving slow, you're going to feel air moving past your hand, but not exceptionally, hard or forcefully. But as the car speeds up, you feel that air blowing against your hand more forcefully. You can feel a stronger force pulling against you. That's not because it's suddenly more windy outside. It's because you're moving more quickly through that air. So you have experienced, if you've ever done that, that force is increasing as your velocity is increasing. So that's where we get that relationship, that proportionality relationship. Now, that being the case, velocity in this case is a derivative. It's dx dt. And if beta is a positive constant, that constant of proportionality, then our force is going to be represented by negative beta dx dt. And the reason for that negative is, like we said, this force, which we call a damping force, is always acting opposite the direction of your velocity. So that means if your velocity is positive, this force should be acting in the negative direction. And if beta is positive, putting a minus here makes that negative. It changes the sign. Similarly, if your velocity is negative, multiplying that by another negative makes it positive. So it's always acting in the opposite direction as the motion of your object. Okay, so what we're going to do is take this term and include it in our model. Remember, before we showed using Newton's second law that m times the second derivative of x was equal to negative kx. And this negative kx here is the net force that takes into account both gravity and the restoring force of the spring. But now our net force is affected by this damping force, so we have to add an additional term here, negative beta dx dt. Moving everything over to the right and then dividing everything by this coefficient m here gives me this dE. Now notice what we have. Once again, we have a linear, homogeneous, second-order differential equation with constant coefficients, because beta, m, and k are all constants. So that means we can solve this one also using the techniques that we learned in section 4.3. But where this is different from what we did in the first part of this section is that we now have a first-order term to consider. Previously, when we didn't have that first-order term, and we also knew that this coefficient was positive, we only had one case to consider. We only needed to solve one case of that homogeneous equation. But it turns out that by including this first order term here, we now have to break this down into three cases. And it's the exact same three cases that we looked at in section 4.3. We solve this thing by setting up an auxiliary equation, but we're going to relabel our coefficients. Remember, k over m we've been defining as omega squared. We're still using that notation here. Beta over m I'm going to call 2 lambda. Okay, and the reason I'm putting the 2 here is not for anything special. I could just call it lambda, but by including the 2 here, once I solve the auxiliary equation for this guy using the quadratic formula, the answer just comes out simpler looking. And that's the whole reason for that. It just makes things a tad simpler algebraically for us. So I can rewrite this as the second derivative of x plus 2 lambda times the first derivative of x plus omega squared x equals 0. Take your auxiliary equation for this and run it through the quadratic formula, and your solutions come out like this: negative lambda plus or minus the square root of lambda squared minus omega squared. And remember that lambda squared minus omega squared there, that is your discriminant. Whether that's positive, negative, or 0 is what determines our three cases. And since we spent a lot of time deriving those those exact same three cases back in 4.3, we don't need to go through big derivations anymore. We're just, relying on what we did back then. But let's look at what those three cases look like in this scenario. So let's first suppose that our discriminant is positive, meaning lambda squared minus omega squared is positive. That would give us two distinct real solutions. And so from what we know about that case, the solution would look like this. Okay, e to the negative lambda t times this guy. Okay, and again, that's just using what we already know from section 4.3 to solve that. Now, this instance where this discriminant is positive, we call this an overdamped system. And what that means, think about what it would mean for this to be positive. Lambda would have to be greater than omega, okay? But where does lambda come from and where does omega come from? Well, they both are being divided by m, but where they differ is the k that influences omega and the beta that influences lambda. Remember, k is your spring constant. So k is in a certain sense a measure of how strong that restoring force of the spring is. Beta comes from your damping force. So beta is a measure of how strong your damping force is. So we think of these two numbers as kind of being in competition. If lambda is the greater of these two, what that means is that beta is large compared to k, which means your damping force is large compared to your restoring force of your spring, hence the name overdamped. Okay? Now, it's important to understand what the motion of this kind of a case looks like. The oscillating, or the motion of this object on the spring is generally smooth and non-oscillatory. I'm going to talk, that basically means it's not going to go up and down, more or less indefinitely. In fact, it's not even going to pass through your equilibrium position. Let's move down here to case 2. So if your discriminant, lambda squared minus omega squared, is equal to 0, then we get this as our solution. And again, that's from 4.3. In this case, we refer to our system as being critically damped. And the reason for that is because these two values are essentially balanced. K is not equal to beta here. Okay, so remember I said that the discriminant here is kind of a measure of how K and B compare to each other. The fact that we're calling this 2 lambda instead of just lambda means that this assumption, this case 2, does not actually imply that these are equal to each other. But think of that as representing balance. They're kind of balanced in a way, but just so. So what that means is if there's a slight change in your damping force, slight change in beta, that's going to take you out of this situation. Okay, so that means we call that critically damped because it's just barely damped enough to have this balance, and any slight change will move you into either case 1 or case 3. All right, case 3, that's when our discriminant is negative. In that case, we'll have this form for our for our system, or for our solution, sorry. And again, that comes straight from 4.3. And we refer to this case as being underdamped because it's the reverse of what we saw in case 1. In this case, the constant K, our spring constant, is large compared to our damping constant, beta. Okay? This motion is oscillatory, it goes up and down. Now, that's because we have these periodic functions here, cosine and sine. It's going to give us that oscillating behavior. One thing that's important to point out, I talk about it in this sentence here, but I'm going to go back to my cases. All three of these solutions have this factor of e to the negative lambda t showing up out here. Lambda is a positive number, so negative lambda would be negative. What that means is that as t tends towards infinity, as time passes, this term gets very, very small and shrinks the output, shrinks the output of this function down, tending towards 0. What that means in the physical sense, remember x of t equals 0, that corresponds to our equilibrium position. That makes sense on an intuitive level. What it's saying is that the damping force is slowing the movement of our object and having it tend toward equilibrium over time. Okay? This video's gotten pretty long, so I'm gonna start a new video to do this example.